Okay. Good morning, everybody. So it's 9:35. We are going to start. My name is Cerneaz. I'm project officer at CINEA, which is the Climate Infrastructure and Networks Executive Agency from the European Commission. And we are here for this session on materials, and we are going to talk about materials and their production processes. So I have with me two speakers. I'm going to that are going to tell us about their project, and I'm going to introduce them one by one as we go along with the session. And then I've also here with me Mr. Bein, Thilo from Fraunhofer, and he's going to moderate the discussion that will follow the presentations. So two projects are going to be presented this morning. One is Fatigue for Light and the other is ALMA. So these are projects that started at the beginning of 2021 and they have just finished. So it's perfect time to hear from the project the results in general, and also considering the fact that this same project were presented last year. So we are going to hear from them what have been achieved during the last year. So the project work on the deployment of lightweight materials, and the aim is of course to help vehicles to improve their efficiency and their range, and we know how this aspect is important in particular for electric vehicles. So we're going to hear first about project ALMA and then project Fatigue for Light. You will have 15 minutes, or as we said, maybe even a little bit more, considering that initially 3 projects were meant to be presented, but we have only 2. So we have time available. There will be the presentations, and then we will have a Q&A session at the end, moderated by Mr. Bein. If you want to ask questions at the end of the presentation about specific aspects that were presented, feel free. So we will very quickly open the floor for the questions, and then at the end we will have this Q&A session. Of course, if you take the floor, please state your name and affiliation. So I propose that we start with project ALMA. So the project is presented by Ms. Ledo. She works for CTAG, which is the Automotive Technology Center of Galicia, where she is head of the Materials Innovation Area. So Ms. Ledo, thank you. The floor is yours. Thank you.
Okay. Good morning, everybody. Good morning thank you for your introduction, Rick. And as he explained, I'm going to speak about ALMA. ALMA was a project, because it finished last week. We have the final review with Salima. And it was a project devoted to develop a new platform or a new body in white for electric vehicles. This was the goal was to reduce the weight and to reduce the environmental impact of the car, and obviously to increase the range. This was the very big goals of this project. So ALMA consortium was composed by 9 partners, led by CETAC, Automotive Technology Center of Galicia, but the other 8 partners, I think it's a very good, I'm sure it was a very good consortium, because we mix the research entities and the industrial partners that for this case I think it's really important. So research entities as TNO, ISWA, Fraunhofer, and CITAC, little companies as Rescol and Innerspec, big companies as ArcelorMittal, Batch, and Ford as OEM. We had around 4 millions, 4.3 millions, and we were 3 years to develop this project. The scope of this project was the structure of the vehicle, the body in white with closures. This was our objective for develop this new structure. The main goal, as I explained, it was to develop a new structure for electric vehicles with reduced weight, with reduced environmental impact and with the big goal to increase the range of the vehicle. For this, our approach was to introduce the eco-design supported by LCA and LCC tools. I'm going to explain. I think ALMA was a very ambitious project because we touched several different points. From one part, as I mentioned, we start with the eco-design. I'm going to go in deep later, but the idea is to have several constraints in terms of lightweight, reduction of the consumption of materials, etc., to be sure that the parts we are developing had the minimum impact in the environmental. Then we work with different advanced materials. In this case, we choose steel, advanced steels developed by Arcelor, and structural SMC, shield material compound developed by BATS. Obviously, all these materials were characterized. We were to simulate the behavior, etc., both for materials and both later for components. We had two innovative technologies concerning deficient separation and the health inspection. That means that, as you know, we think that the very best solution for having an innovative structure is to combine materials, the multi-material. So we always say the right material in the right place. And this is fantastic, but you have to join these materials, and at the end of life of the project, you have to disassemble these materials. So we work with our partner Riscol in an efficient separation technology. It was based in the use of an adhesive that when we apply a very high temperature, at the end of life of the vehicle, obviously, very high temperature, it means around 200, 250 degrees, the adhesive disappears, so the different parts can disassemble easily. In the case of the structural health inspection, is based in a mix of ultrasound and radio waves that are able to identify if there is some bubbles or some cracks in the composite parts and always in the steel parts. So we are able to identify during the life of the vehicle if some part is damaged or not, and we have to repair or not. Obviously, it's really important to be sure that the new materials can be recycled. So TNO was the partner devoted to this question. And when we talk about a new platform, a new structure for the vehicle, we had to be sure that all these parameters, all these new parts are working well together. So we need to simulate the parts, the subsystems, but obviously the full vehicle. So for CITAC and Fraunhofer was responsible for this validation. And we had also some physical prototypes to be sure that all the design is also feasible, and we are able to manufacture these parts. So as I mentioned, very ambitious project, touching many different questions, and the big goals were to decrease the weight in 15%, more or less, concerning the baseline, and to improve in 11% the LCA, the environment impact. Okay, this was the objective, so we started. We started with the eco-design, but as I mentioned before, supported by LCA and LCC. So, first point, we have several constraints. Several constraints due to the materials we are using, but also the constraints we have due to the structure we are developing. So We have to develop a new structure, but this is mandatory to pass all the crash. So the behavior of this new structure should meet all the requirements we have for the automotive sector. The cost is important also. I always repeat that we are in the automotive sector, so for us, the money, the cost is a constraint itself. So we are approaching this project for lightweighting, but the cost is important, and the quantity we put was 3 kilos by Eurosave. It's not a quantity I said, it's the market, the OEMs who put this quantity. So materials, I repeat, several different grades from steel and SMC materials. And with this constraint, we have a first bill of materials. And, but we have to select, we have to define what are the best. I mean, there are several parts that is really clear that steel, different grades of steel, are the best option. There are others that SMC materials are the best option. And there are others that we have a competition between these two types. So we define a material matrix. I have no time to enter in the detail, but you can guess that we put several factors to decide. Several factors as lightweight, cost, feasibility to introduce in the production line, etc. And we have also a very useful tool, BEPSIM. BEPSIM tool was developed by TNO, our partner TNO. And BEPSIM, if you search in Google, it's very easy to access. BEPSIM is a LCA tool and not. I mean, LCA tools is typical that you need to know, to have a very big knowledge about LCA to have results. In this case, it's a very simple tool focused to be used by designers. So it's very friendly, it's very used, and with several easy steps, you are able to identify what are the good solutions, the good selection of material, the good design. So we use this tool to support our design. So we have the materials, we have the design, and we go to the crash simulation. I told you before, we have to pass absolutely all the requirements we have in the vehicle. Frontal crash, lateral crash, with different angles, etc. If always works well, at first time, it's impossible or very, very difficult. We have to repeat the process. So we repeat the process, I don't remember how many times, but several times, obviously. And at the end, we have the final design that are meeting all the requirements. So I talked before about the materials, these advanced steel materials and the structural MC. More part of the vehicle was developed for steels, obviously, and we choose finally the SMC for the dash panel and for the battery lid. In the case of door panel and the door panel and the H-frame was also manufactured because I mentioned before, we want to validate all the structure, all the body in white by simulation, by virtual simulation, but we want to be sure that these new materials were able to manufacture. So we carry out the manufacturing of these two parts. It's important to mention that I think I don't mention that our baseline was the Ford Mondeo, IC, and now we have a platform or a body in white for a Ford Mondeo full electric. It's important to mention that these two parts, the H-frame and the door panel, originally were composed by several parts. I mean, the H-frame was composed by, I think, 15, 17 parts, and the door panel by 4 parts. And now it's only 1 part. That is due to the different steels that we are able to process at the same time in one shot. So you can guess that to integrate these functions, it's a good solution to avoid joints, to avoid extra weight. And in the case of the dash panel, we have the prototype in SMC, physical prototype, I mean. So I mentioned before, it's important to be sure that all these materials are recyclable. And in the case of the standard steel, it's clear, it's recyclable. But we have a grade of steel that it was laminate, steel, thermoplastic steel. So we have to be sure that we are able to separate and to process. And yes, it works. And in the case of SMC materials, as you know, we have thermoset material, resin, and fiber, so we need to be sure that we can separate always. So people from TNO apply different technologies, solviolysis, mechanical recycling, and we can verify that it's right and it's okay, like we can separate these different materials. I mentioned before the 2 different technologies to be sure that we can separate different parts that are joined by structural joining. And in the case of the system monitoring, that we can be sure after a crash, for example, that to be sure that one part is right or not, and we can reuse or not. During these 3 years, we work in the design, we work in the manufacturability, we work in the recycling, and at the end, we achieve a 22% weight reduction. Our objective, if you remind, was 15, so we are proud of this value. And this was the final prototype where all the design was integrated with these new steels from Arcelor and the new dashboard from SMC. So, well, I think the results are really good. We can be sure that these new materials work properly, and we can have a new body in white, a new structure with guarantees to meet all the requirements. If we talk about the different cooperation with other projects, in this when we apply this topic 4 years ago, there are other 4 projects that were also funded by the European Commission. This was Levis, Flamingo, Revolution, and Fatigue for Light, that speak later, my colleague. And we were joined in the Enlight electric vehicle cluster. That this consortium from different projects help us to understand how many different approaches can be used to go to the same objective. We can learn the different results from other projects, so we think it was really useful to collaborate in this case with these sister projects. We always participate in different congress fairs. We had our last event in the Global Automotive Components and Supplies, Stuttgart last year, showing our parts. So I always say that the technical work is important, but to disseminate and communicate not only in today for technical people that maybe already know this type of projects, but other people that don't know projects that are realizing in this area. And the impact is not always easy to define. When a project ends, to define, okay, and now what is the impact I'm going to have my results in the future? Well, I think we can define that the adoption of the eco-design strategies in the automotive sector is already here. we are already applying for different OEMs, so I think it's really important. Bein is, we are sure that is a useful tool that help the designers to go in deep. I mentioned before 22% weight reduction was the quantity achieved. That means that translates in a reduction of 24% in terms of environmental impact, if we talk about emissions, CO2 emissions. And all this goes to increase in 6% approximately the range of the vehicle. Industrial partners are not here for Arcelor and BAT, but last week in our last meeting, they explained that they think that in the future, not tomorrow, but in the midterm, in some years, these new materials and these new strategies for the design will be included in the new cars. So we think it's a good news. And now there is a video. I don't know if you can go. Yeah, that is. Thank you, Xavier. It's a very brief summary.
Road transport accounts for 24% of the EU's total emissions from carbon dioxide. In response to this environmental challenge, the EU Green Deal is committed to decarbonize this sector, targeting a 90% reduction in emissions by 2050. The ALMA project plays a critical role in this transformation, which involves a significant shift from fossil fuels to electric vehicles that are lightweight, efficient, and sustainable. By using advanced materials and an eco-design approach, the body in white of ALMA's concept car achieved a 22% weight reduction compared to the baseline BEV body in white. This translates to a substantial 24% decrease in carbon emissions over the car's entire service life. Innovative use of advanced, high-strength steels and lightweight laminates can revolutionize vehicle structures. The integration of advanced steels enabled the new H-frame concept, reducing parts from 11 to 1, decreasing the vehicle's weight and production costs. In some cases, sheet-molded composites with fiber-reinforced textiles can replace steel for even greater weight and CO2 savings, while maintaining similar structural performance. ALMA's eco-design approach not only emphasizes weight reduction, but also focuses on circular economy aspects. This includes strategies for easy assembly and disassembly, efficient recycling, and end-of-life material separation. Rigorous safety and performance standards are validated using multi-scale characterization through computer simulations. These were used in simulated crash scenarios, allowing engineers to quickly test alternative designs and iteratively improve the concept, saving time. ALMA's approach to eco-design involves complex trade-offs. While some materials offer sustainability during usage, their production and end-of-life phases might cost more environmentally. The BEV Sim tool makes comprehensive life cycle analysis and cost assessments easily accessible to designers and engineers. Continuous structural monitoring is another key component which will allow for early fault detection and preventing critical failures. This enhances both vehicle safety and longevity. For end-of-life scenarios, ALMA applied debondable adhesive for efficient separation of materials through heat triggering. ALMA identified potential routes for recycling and recovery of advanced materials, including pyrolysis and solvolysis, paving the way for more circular manufacturing. In conclusion, the ALMA eco-design integrates with current automotive manufacturing processes, making it readily adoptable by the industry. You too can use this approach and advanced materials to increase range and performance while saving materials, energy, and CO2 emissions.
I think it's a best summary than I can speak. From my part, it's all. Thank you very much.
Okay, thank you. Thank you very much, Ms. Lena. Very interesting presentation. Also, I can say that it was also interesting to hear from you your experience with the cluster, with the light EV cluster. which is something that I haven't heard in other presentation. I think is good to report also this experience that you had. Okay, so we now jump to the next speaker. So our next speaker is Miss Barbu, Lucia. She's assistant professor at UPC, so the Polytechnic University of Catalonia, and assistant research professor at the International Center for Numerical Methods in Engineering, so CINEA in Spain. And CINEA is as well the entity in charge of the coordination of the project Fatigue for Light. So, Ms. Barbu, the floor is yours.
Thank you very much. Thank you very much for the kind introduction. Okay, welcome everybody. Thank you for attending this session. Let's hear some interesting news, some interesting facts about the Fatigue for Light project. Okay, now we were funded under the GV06 2020 call. Okay, so it's an innovation action. So of course, I would say the biggest weight in our consortium goes to industry. We have several industrial companies in our consortium, 3 research institutions, 3 universities, and 1 standardization body that will help us standardize some very interesting experimental procedures we developed in the project. Here you can see the members, the partners forming our consortium. Of course, as our chair already said, the project lasted 3 years. We just finished working this past January. And we were funded approximately with 5 million euros by the European Commission. We gratefully acknowledge the support, with a total budget of 5.5 million. Coordination by CINEA, which stands for International Center for Numerical Methods in Engineering in Barcelona, in Spain, where I work. Okay, but we are not only company logos and not only numbers, we are also people, okay, behind the consortium. And here you can see all of us at the last consortium meeting, which was held just this past January. You can see that after 3 years of work, we have, I think, some more gray hairs and some stress lines, but other than that, we are in quite good shape, I would say. Okay, let's review a little bit the objectives for the Fatigue for Light project. So the main objective, I would say, as stated by the call, was to reduce vehicle chassis weight. Chassis, because the Fatigue for Light project is targeting specifically the chassis performance, okay? But another keyword, I would say, which is also in the title of the project, is, apart from chassis, fatigue performance. So a very big part of our work plan was devoted to developing new tests and new computer simulation methods which were used to assess the fatigue behavior of chassis components. Okay, of course, we wanted to foster the implementation of new materials, which can give an interesting weight reduction potential, I would say. And we were committed to using eco-design and circular economy aspects while we were performing this lightweight assessment on the chassis components. Here you can see our first project video. We have a new one, by the way.
The chassis of an electric vehicle accounts for 50% of its weight. What if we could reduce the weight and thus increase the vehicle range while contributing to a more sustainable mobility? Lightweight materials have been around for some time, with great potential in reducing the vehicle's weight without compromising safety. However, they introduce significant challenges related to part design and performance prediction. To solve these challenges, the Fatigue for Light project develops innovative computer modeling tests and experimental methodologies to select the optimal materials for lighter vehicle chassis and reduce the testing time for new materials. Based on eco-design and circular economy values, Fatigue for Light aims to boost the use of lightweight materials adapted to the chassis parts of electric vehicles, enhancing weight reduction while increasing vehicle safety. As one of the first projects tackling weight reduction in electric vehicles' chassis parts, Fatigue for Light takes a step to make advancements in building a zero-emission future, while simultaneously minimizing production losses and meeting the industry needs. To find out more about the Fatigue for Light project, visit our website www.fatigueforlight.eu or follow us on social media.
Because we have some very interesting developments, okay, in the project. I will present today a little bit from above the perspective. I don't have much time to get into details, but if you are interested in anything that we've done in these past 3 years, visit our website, visit our YouTube channel. There's a lot of information there, okay, on how we can collaborate. Let's go to results presentation. So here I'm going to show results from several different perspectives. And first I want to share with you all the work that we've done experimentally from the experimental point of view. Several teams were intensely working these past 3 years on several different campaigns at different levels, at different scales. And we started thinking at coupon scale about how we wanted to reduce the experimental time needed for a complete, comprehensive fatigue experimental characterization. Now, I don't know if you are familiar with all that fatigue entails, but I would say one of the main characteristics when you are dealing with fatigue is that you need to have a very, very thorough experimental campaign to consider that you have properly characterized your material. And that means you need to spend a lot of time experimentally. Fatigue tests are super, super expensive, okay? This is why we devoted a lot of time in the project working on fast fatigue characterization procedures. Okay, these are fast fatigue tests that allow you to spend from maybe 1 month that you had devoted to obtaining your SN curve, which is stress number of cycles curve. You can spend it as less as 2 days for one SN curve, or if you are only interested in the concept of fatigue limit and you only want to know your fatigue limit, you can have it in 4 hours. So the reduction in experimental time really is quite significant, okay? We developed 3 different methods. Here I can show you details only for the damage control method, or what we call stiffness monitoring method. But we also have the self-heating method, which was developed by our partner Arcelor, and we also have the ultrasonic testing procedure, which was developed by the Politecnico di Torino, a partner in our consortium also, for very high cycle fatigue specifically. Okay, if you want more details, we have published papers on this. You can have all the information available there. Okay, after that we went to a second experimental block, I would say, where we were focused on the manufacturing effects on the behavior and the performance of fatigue. Okay, so chassis components, they are manufactured obviously using quite standard, I would say, procedures, so that punching, trimming, forming, welding, all of these you will find habitually used on chassis components, right? And we wanted to know, okay, but the effects that these manufacturing processes generate in your component, the nonlinear effects that they generate, how are they influencing the fatigue performance afterwards? And here you can see, for instance, some SN curves that we derived on these punched, formed specimens, etc. After this campaign, we wanted to complicate a little bit more, okay, the problem. So we went to a slightly more complex geometry, not just coupon scale, and we went to a lab scale demonstrator. Here we chose an L-shaped profile, and we wanted to compare the performance in between a fully polished specimen and a geometry where we had some rough edges and we had some punched holes that were not, I would say, they didn't have their surface treated, right? They were not polished. And here you can see the results, for instance, from the experimental campaign made on this L-shaped profile. The last year of the project, it was devoted, of course, on experimental tests at component level. So we had several different components that we tested their performance in our project. And here you can see the test setup for a lower control arm. This is the steel version, and here we have the hybrid version, which is a multi-material solution. Here you can see a cross-member beam and the test setup for this. And all of these tests, they were super important for us to find out how the numerical modeling we developed in the project was able to capture this experimental performance. And now, this is the perfect opportunity to speak about the other line that we followed in the project, which is the numerical modeling approach, okay? And as I said, keyword for our project, fatigue performance. So the numerical modeling we developed was specifically targeting the fatigue behavior, and specifically the whole process of degradation which occurs under cyclic loading from crack initiation until the complete failure of the specimen. And I'm mentioning this because this is definitely something that you cannot find in standard fatigue tools that you have available in the industry that industrial companies use. Why? Because there are a lot of plugins which are used for solving fatigue, such as ENCODE, FEMFAT, a lot of them, very famous, and they do a great job. But they will only give you an elastic response, okay, and they will only predict when damage starts on your geometry, at which number of cycles, of course, and where, okay? But they won't tell you what happens once that damage initiated. Maybe it will take you to complete failure, of course, but maybe it will last 100,000 cycles until you reach complete failure. How do you know if the damage initiation has been critical for your component or not? Okay, so we worked on the fatigue approach, modeling approach in this project to provide a full deterioration progression, okay, at component level. That was our target and that was our objective. Okay, apart from that, we were very interested, of course, in assessing the fatigue from a comprehensive perspective, in the sense that we wanted to also prove that we were able to capture the load sequence effect, which is very important because your components are not going to be subjected to the same cyclic load with constant amplitude throughout their entire life, obviously, right? You're going to have some dissipation events over there that are going to do some nonlinear effects, maybe plasticity. After that, you will continue with a different type of cyclic loading. A lot of things can happen on your component, okay? We wanted to also check the residual strength analysis, what happened when you applied a specific number of cycles of loading, and after that you failed the material. Did it fail out at the same level of load as its initial strength or not? Not. The answer is not. And also overload phenomena. Okay, now this analysis was done. What I'm showing here, by the way, is the results from the numerical simulations at component level. Okay, obviously we simulated coupon level, we simulated lab scale demonstrator, but in the interest of showing you, I would say the most spectacular result, we wanted to show only the coupon level. And here, if I manage to click on this video somehow, okay, I will put what I can. You can see the crack propagation occurring, for instance, for this welding simulation, which was done on a lower control arm, okay? And here, maybe I can capture this also. No, I can't capture it. Ah, yeah. Yes. You can see here, for instance, this very interesting failure, which was obtained with a primary crack and then a secondary crack under fatigue at about, it started propagating at about 19,000 cycles, and after that, it failed completely at 25,000 cycles, okay? And this was analysis, a numerical analysis done on the lower control arm. After that, of course, we had another numerical campaign, which was done on the wheel. And what we are always comparing from the numerical point of view is the failure location, okay? So the presence of the nonlinear effect on a geometry in the numerical simulation as compared to the experimental test, and it was in very good agreement. And after that, of course, if the numerical simulation is capable of predicting the actual fatigue life which was observed in the experiment. If not, it doesn't help, we don't provide any type of usefulness, I would say, to the industry. And again, we got a very good agreement in between the numerical and the experimental part. We had a different demonstrator also, which came from the heavy-duty vehicles part. We had the cross-member beam, and this demonstrator was loaded in different directions with cyclic loading. And here I can show you the simulations with the crack propagation for the load being applied in two different directions. And again, a comparison of the life obtained numerically versus the experimental result, and we again saw that we had a very good agreement here. Okay, so we did some experimental tests, we did some numerical simulation, but in the end the purpose was to reduce weight. Okay, so how did the different material solution that we focused on, we studied in the project, how did they perform as compared to what is normally done state-of-the-art on these components? For instance, for the lower control arm, you can see here that we manufactured two different versions. One was CP980, complex phase of 1000, and the other version was in a hybrid multi-material solution. What we saw for the CP900 was we could get a weight reduction of about 12% with no performance loss. However, if we took into account also the design optimization process, we could take it further up into 20%. Regarding the multi-material version for this lower control arm, we got a very good weight reduction, about 35% potential. So that's good, but that's not everything. I will speak later on about more about this. Regarding the campaign on the wheel, disc plus rim, okay? We studied the performance of a demonstrator which was manufactured with CP800. And we saw that the weight reduction we were able to achieve on this demonstrator was only 5%. And this gave us a little bit of thought, and we started to think, how could we somehow improve the performance of this material for this demonstrator and perhaps enhance the weight reduction? So we started to focus on surface treatments that could help us get a better fatigue performance. So in this sense, we manufactured and tested another demonstrator in CP800 with shot pinning on disk only, and we saw that it allowed such an improvement of the performance for fatigue that it further allowed us to reduce the thickness and reduce the weight associated up to 9%. Then, regarding the cross-member beam, the material which we proposed as an innovation for this type of demonstrator was the 22 manganese boron 5, which is the press-hardened steel. And we eventually saw that this was a very good choice because it enabled a weight reduction of about 43%, which shows how promising this material really is for heavy-duty electric vehicle chassis. Okay, so I've shown you weight reduction. Is weight reduction everything? Should I just stick with the maximum value I get here, which is the hybrid solution, the multi-material solution, and just say, great, I'm going to manufacture my chassis in this multi-material solution because look at all the amount of weight I'm going to reduce? Well, obviously, no, okay? Because there are a lot of aspects that you need to consider. Specifically, if you're thinking from an eco-design perspective, obviously you're interested in how much you reduce the CO2 emissions, end-of-life considerants, recyclability, etc. Okay, so from this point of view, this adds a whole new dimension, okay, to these results that you see over here, and we have some very interesting results in the project that we really want to share with the entire industrial community and the entire European Commission community, which will show what's the best performance when you compare several different aspects. For instance, we had a technical block where you obviously take into account and you rank the technical performance of the materials. We had a second block, which was the eco-design or the sustainability block, so where you take into account the weight reduction, you take into account the CO2 emission reduction, etc., etc. And we had a third block, which is the economic aspects. Obviously, cost is super important. You can have a great solution, but if it's super expensive, it's not going to get into I would say, middle range vehicles. It's only going to go into the premium ones, right? But the analysis from this multi-criteria point of view will give you a different idea with respect to the performance of these material solutions. And this is something that we will publish in the future. So please follow us and check our publications, okay? Okay, so let's have an overview of the technical achievement. As I said, we moved through different scales: coupon scale, lab scale, component scale. But the purpose was to discuss about vehicle scale, right? So all of this served into taking us to an estimation of the weight reduction that we were able to achieve with the procedures developed in the project at vehicle level. So we were specifically interested in how much we were able to reduce the structural weight of the vehicle, and here we considered as a structural weight the chassis and also the body in white, which leads us to about a 55% of the weight of the entire vehicle. And when discussing about this, what we were interested in is seeing how the weight reduced if we directly substituted those materials which were currently state-of-the-art for our components with the materials that we studied in the project, and we assessed comprehensively from all of these different scales point of view. So in the project we studied, of course, the CP800 for applications where it was not already state-of-the-art, then the CP980 for some other applications, the press-hardened steel, a specific stainless steel, 2 different aluminum alloys with Series 6, and of course the multi-material solution with these 2 outer layers of aluminum and an inner core of glass fiber reinforced polymer. And another solution that I haven't spoken here, but it was also studied in our project, the carbon fiber reinforced polymer solution. Okay, so if you directly substitute the materials which are made now in a specific state-of-the-art on specific components, and you substitute them with these materials that we studied in the project, what we saw that you could obtain with this direct transition, I would say, a 15% weight reduction after using fatigue for light materials. But as I said, this is taking into account only the substitution of specific components which are super easily to be replaced. However, If you afterwards do a lightweight average, I would say, at the whole structural weight of the vehicle, the overall reduction is lowered, so you can only get to an average of 10% reduction over the whole structural weight. And this, I have to say, is only taking into account components which are manufactured from steel sheets, but you have a lot of different types of components, and they are not always manufactured from steel sheets. So if you evaluate the potential lightweight for all chassis and for whole body and white flat steel components, you can get to about a 30% reduction in the weight, and this number was achieved considering that you could get an approximately 5% lightweight potential on other metals, which was thanks to the improvement that you got in simulation due to this procedure that we developed in the project, okay? Okay, now let's switch topic, okay? We worked a lot in these past 3 years on dissemination because we wanted to take the message of everything that we were developing in the project as much as possible to a very large community. So I don't know if you heard about our project before coming to this session. If you did, then we did a good job disseminating, and if you didn't, then we still have some additional work to do. But basically what we focused on was a lot of scientific publication. We have currently 13, but there are still about 3 which will be published soon. They are under review. We had a lot of dissemination events, conferences, congresses, workshops, a lot of specific project events, 3 webinars, then 2 cluster webinars together with our sister projects in the cluster that we formed. We had 1 physical workshop with key companies in the industry, super interesting. We could get some perspectives on what they thought about our development. And we had a final project conference where we shared more in detail, I would say, the work done in the project. And I'm mentioning this right now because a lot of the materials from these events, they are available online. So if you're interested in a specific development from our project, look for our YouTube channel, look for these events. They are accessible from the webpage of the project, and you will find the presentations, you will find the backup for these presentations available for you to check, okay? Standardization, very important, because we said we developed these fast experimental fatigue procedures. Okay, but we want to make them available to a really large community that might find them useful. You can't do this if you don't have them standardized, okay? So we've worked intensely on a standardization procedure in our project, and we are very close to getting a standardization agreement on 2 different types of fast fatigue experimental testing. One of them is the self-heating measurements promoted by ArcelorMittal, and the other one is the rapid fatigue testing by damage control promoted by Eurecat. Okay, regarding project website and social media, a lot of information that you can find on our website. We have a lot of videos where we explain things about our project. So take a look, check if there's something there that might interest you. We are available to discuss anything you might need. Okay, mid to long-term expected impacts of the project. How does the Fatigue for Light project impact the industrial community, and I would say the community in general? Well, first, we developed, we analyzed the performance of new materials, okay, in our project, which we saw that they had a very interesting weight reduction potential, okay? So this was definitely something to consider when you're analyzing potential innovation for your chassis component. Then, regarding the fast experimental techniques that we worked on and the numerical modeling techniques that we worked on, they are obviously useful tools if you want to have a smart design of vehicle components, okay? So this is another impact that we are bringing to the table. Increased efficiency in vehicle development. Do we manage to have this impact? Yes, because of the numerical modeling, which serves as a tool for you, for the industrial community, to detect when nonlinear processes are going to initiate in the geometry and how they are going to propagate until total failure. And new experimental tools, which, as I said, will help you significantly reduce the experimental time you devote on fatigue characterization specifically. Then, structural integrity procedures. We are targeting this by the sensoring that we did in the project on specific components, and this will help monitor what is the performance of your component, what's the structural integrity of your component, obviously, and based on the fatigue assessment on lightweight solutions. My presentation got a little bit disarranged, I would say, but it is what it is. You will be able to fulfill this impact, because if you use this fatigue numerical modeling that we developed in the project, and you know how the degradation process is actually going to occur due to the cyclic loading on your geometry, that will help you make better informed decisions regarding your maintenance schedule. Do you have to switch a specific component at the first sign of damage initiation? Maybe you do, of course, but maybe you don't. How do you know? Well, if you use a tool that will help you decide, okay? Okay, effective solutions for reuse, recycling, and recovery of materials. Here, the team at RISE, Research Institute of Sweden, a partner in our consortium, worked to propose a dismantling technique for the hybrid solution, the multi-material solution of the lower control arm, okay? Now, regarding European policy objectives, well, Fatigue for Light is contributing to a more competitive and smarter Europe because of these tools that we've developed in the project, which can help you obviously to have a faster and optimized design. How are we helping to achieve a greener net zero carbon economy? Well, use these tools that we've developed. I'm repeating myself a lot, but they are really useful on so many different levels, okay? You are going to be able to reduce weight. If you reduce weight, you can lower the fuel expense, or you can increase the range. Either way, you have some win-win situations over there. A more connected Europe by enhancing mobility. Yes, because if you have a more efficient design, you can, obviously this takes to reduce costs, and this can make the solutions that you are offering to the consumers more accessible. They can make them cheaper, okay? So more people can have really amazing cars and drive them happily on the road. Okay, nothing more from my side. Thank you very much for your attention. I'm here if you have any questions regarding the work that we've done. Thank you.
Okay, thank you. Thank you very much. So we had an overview of how we could achieve weight reduction with the structure of the vehicle. So first presentation of on how we could do it on the body in white. Second presentation about how can be done on the chassis components. So I now leave the floor to Mr. Bein for the question and answers session.
Yeah. Thanks a lot, Eric. I'm taking over. Yeah, first of all, also thank you very much for the nice presentation, Raquel and Lucia. It was quite interesting. Are there any questions from the audience? I hope so. Yeah.
Christoph Czarnos from FAV and also ALPA president. So you showed like exchanging standard parts in your body in white and in the structure by, for example, high strength steels or by compound materials. What has to change in the scrap yards with the treatment of disused vehicles to avoid downgrading of the materials that you recycle?
I have not this data here. I'm not sure to answer, but the idea is to reduce at maximum both in the material manufacturability, but also in the parts. But I'm not sure. At this moment, I'm not able to give you a data about this. But I can translate your question, and I can.
What I would like to add here is just, I would say, a common sense answer, I'm afraid. But I would say just to make them technologically more advanced, because I believe that nowadays the scrapyards, the graveyards for our cars, they are not really digitalized places, and there's not a lot of technology you have over there for dismantling purposes. So obviously from the research point of view, we are studying these advanced recycling processes and dismantling processes and downgrading processes. But if you don't take them to the lowest level, which is there by I think quite a significant investment, in technology line, we are not going to have any significant impact on this point, at least.
Only it's not fully linked, but maybe with the new standards, the new normative for the future, as you probably know, we are going to need to have a label in all the materials and all the parts. So it's clear that this normative, this new standard, is pushing to be sure that how many material is coming from recycled material, and what are the quantities you are losing. So it's clear that in the future, in the next future, we are going to have much more information about it, and we are going to know exactly how many material parts are scrap or not. But currently, I agree with Lucia, it's not easy to say.
I mean, you would need a detailed passport of the digital passport of that vehicle, yeah? Like a digital twin that maybe you also would have to maintain over lifetime in case the car undergoes a repair and maybe some third party, let's say, non-original spare parts are mounted or whatever. Yeah?
Yeah, so there's definitely research needed. Based on this question, what, from your experience within the project, would you prefer mono-material solution or hybrid or multi-material solutions in terms of end-of-life strategy?
In terms of life, the easy solution is the monomaterial. It's clear, but now we are seeing that the multi-material option is the good one to achieve the targets of weight reduction, environmental impact. But so we have to go to a balance between the easy solution for dismantling or the best solution to meet the requirements.
Yeah, this brings me to one of the questions. Sorry for this. It's my topic I'm currently working on. You showed the example of the sheet molding compounds, SMCs, and you say as a recycling strategy is pyrolysis or general treatment. So this is some kind of losses. Did you calculate the environmental footprint? So basically the selection of technology should be by an assessment of the cradle-to-cradle approach.
I'm not sure, but I think the calculus we had, it was from cradle to cradle. But,
but pyrolysis is not considered as very environmental friendly.
Yeah, but it's true. For example, in this case, the fiber used to reinforce, the textile used to reinforce, it was from pattern, we can say, but we know that there are other fibers or natural fibers, so we can improve in this case if we need. We have the potential to improve. But it's not the good option to recycle. It's true.
Yeah, we faced similar problems with the cross control arm in SMC manufacturing, that the balance was not optimal, I would say. Further questions? Yeah, Mr. Lehmann.
I would have two questions. I'm not an expert on this. Materials, products, production processes. You develop very nice tools for predicting fatigue. These are simulation tools, and I guess they are nice to fit with the current software, but how you maintain, how can they be evolved, because software is not static. It always needs to be adapted. How is that process that in a few years, or who is taking that one up? That's the first question. The second, in projects, there's often an advisory board, or used to be an advisory board. And I find that very helpful in the projects I have. So how did the advisory board guide you, help you? Can you elaborate a little bit on that benefits of the advisory board?
Okay, so let me focus first on the first question regarding the software.
Your microphone is not on.
Yeah, it's not on?
It's on?
Yeah. Maybe I need to bring it closer. No? Okay, great. Okay, so software solutions, yes, definitely. They are a living creature. Okay, so they're evolving over time. At the moment, the numerical formulation targeting fatigue we developed in the project is implemented in an open source code, which is developed jointly in between several different institutions. CINEA, the place where I work, is definitely one of them. I would say the main developer, but also TUM, Technical University of Munich, has a significant group of developers working on this code. Some commercial companies are also interested in this, like Altair, for instance, with the hypermesh, and they're very big and famous. They have quite a lot of developers working on this. So how do we bring this to companies? How do we maintain it long term? This is not a software that was invented yesterday, I would say. The solution is implemented, by the way, in Kratos Multiphysics. I don't know if you've heard of the software, if you're familiar with it. But Kratos Multiphysics has quite a long history being maintained and kept up to date. And since we have this, there are about 150 developers nowadays working on software. So it's really a big software. It's not just something small that we did, for the project. And once the project finishes, we just put it in a drawer and everybody forgets. Because I would say that's the main risk when you're dealing with numerical modeling. It's a software that has quite a long life ahead of it. And obviously we are working to improve it, optimize it, make it as competitive as possible with the commercial solutions that have, insane sales teams and commercial teams that are going to tell you that they are the best, softwares there are in the world, okay? So firsthand, I would say we are continuously working. We guarantee a high amount of developers which are working to maintain and make this software competitive. And you will find us 5 years from now working on this. You will find us 10 years from now. Actually, that's my research line, fatigue, and numerical simulation of fatigue. And I plan to not go out of business very soon because I'm quite young yet. And I hope I still have about 10, 20 years of life working on fatigue numerical behavior. Ideally, someday, we are going to wrap it with a super nice interface, and I'm going to contact the sales team, and they're going to come and sell to you the Kratos numerical solution. Okay, maybe I'm going to call it something else. I don't know. The second question about the advisory board. That's a very interesting question. In the project, we didn't have an official advisory board, okay, an official committee that I can give you with a list of names that helped us. But ever since we started developing the Fatigue for Light idea, which in the beginning was just, the consortium formation and building the work plan and what were the targets we wanted to achieve and how we were going to develop them, we had a lot of experts. Obviously, the partners in the consortium are the first interested, right, in helping and in providing their perspective and in telling us if what we were proposing from the research side was actually interesting for the industry or not. Because research-wise, you can do a lot of things, but what actually is useful for the industry and what they eventually are able to use and implement in their procedures, that's a different business. Okay, so from this point of view, I would say our main advisory board was the consortium. And when we pitched the idea to several different partners, because we were looking for partners interested in forming our consortium, again, we had some interesting feedbacks from a lot of different companies that helped us. I'm not going to say names, okay? But we had access to a lot of industry and their feedback. Some positive, some negative at the beginning of our project, which I'm hoping now, after we worked and we developed some hands-on solution and we showed how we can bring innovation in the fatigue behavior, they're going to a bit change their perspective on our proposal. And I wanted to say something else regarding this. Yes, some very interesting things, in our project, we targeted specifically the innovation on wheels, and we proposed these new materials, these new techniques on wheels. But what I want to mention here is that I think chassis in general, but specifically wheels, they are a component which is so optimized, it's so it's widely produced. Come on, like a production line with millions of units, okay? There was no innovation done on wheels since 1997. And with our project, we managed to offer a solution which they are going to implement in their production line in the next year. So really what we did is effective, it's efficient. You can use it if you put your mind to it. Okay, thank you.
Thank you, Lucia, for the, yes. Yeah, sorry.
Only one comment concerning the advisory boards. In this case, in ALMA project, it was similar to Lucia explains that is not directly involved, but in other projects we have. From my point of view, it's always positive. For example, I work in Automotive Technology Center in Galicia, so we work with we can say, with the top 10 OEMs at Europe level and the top 20 Tier 1, Tier 2. So all the information, all the requirements they provide us are interesting, obviously, but it's clear that they have different priorities and different interests. So the good solution for Stellantis maybe is not the good solution for Ford or for Volvo, but it's clear that to have all these different opinions, all these different suggestions, it's always useful for us. So in other projects, we have a more active advisory board, and we think it's useful to be sure that, okay, maybe we are not aligned with the 100%, but 70% of the industry is agree with this line and is interesting. So it's always important to not lose the final objective in this type of projects. It's clear.
Okay, further question from the audience. There is one in the back.
Hello everyone, I'm Victor Demo from Plusidiada. I have a question for ALMA project. You showed the new H-frame that you developed that is now in one piece and not instead of 11, you said, or something like this. I wanted to ask if in case of, for example, in a real life crash, for a real crash, let's say, what is how do you repair this part, let's say? Because at the end it's all the rerun structure, and how does, if the cost is the same as before, or do you want some, if you have to to repair it, if it's if you show you have seen this on your project?
Yeah, I think at the end is not we have not an extra cost concerning the current cost, because if you have a crash and you have to change all the H-frame or the door panel, we have to change in any case. It was made from one part, as in this case, or it was made from 4 different parts. So the saving cost we obtain when we manufacture the first time is there, and then there are not extra costs. So I think is the best solution, because the saving when we have avoid all the joints, all the extra welding points, etc. Is it works, we can say, and for repair is not more difficult, we can say.
Okay, thank you.
Further questions? I have 2 rounds of questions for you. I think we are all facing similar problems in project like this to, let's say, assess the impact of your technical solution, which you demonstrated on component level or part level on full vehicle level, in terms of weight saving and in terms of cost. What are your experiences with that, and how did you do it to come to a reliable assessment on the impact on the overall weight reduction? Who wants?
I can start answering. For us, it was definitely a challenge, because the whole work plan that we thought in the project was completely focused on components. Yeah. So when we got to the vehicle extrapolation, I would say, the first good news is that you can do a vehicle extrapolation, because sometimes with the techniques that you develop, I don't know if it's that easy to extrapolate. But numerical simulation, if you apply it on a component or on another one, you can find a lot of components throughout the vehicle that you can apply it to first. And how did we reach this I would say this fancy number at the vehicle level? Well, we based in the Fatigue for Light project, we based this approximation, this extrapolation on the OEM experience that we had in our consortium. So we followed the guide to do this procedure was in our case Stellantis, CRF. And based on their experience with a specific vehicle they had in mind, with a specific chassis and body in white, obviously they know the detailed information for all the parts, the material, what can be substituted easily, and what is not so feasible to be substituted, and they helped us in our
But you did not perform redesign and crash simulation?
No, and that's an important part, because I would say a lot of people that are working in the automotive, a lot of projects that are working in the automotive domain are focused on crash. In our case for Fatigue for Light, this was not taken into account. Maybe in a follow-up we can target also crash, but first I would say for body and white, definitely crash is your breaking point, I would say, right? Or what ends up dimensioning your body and white. For chassis, You obviously need to have structural integrity under crash, but fatigue is also a super important case that you need to pass, evaluation that you need to pass. So from my case, I would say crash was not that
yeah, but if you transfer to the body in white, then you have to consider crash.
Yeah.
And then it's
here's where ALMA.
and about the costs.
About the costs.
Yeah.
Cost consideration.
Cost consideration.
Again, we had several different lines of work in the project, and one of them was the life cycle assessment and life cycle costing. And we had partners which were working on that and developing a specific eco-design methodology targeting component levels, and obviously working super close with the industrial partners, which can tell you the different levels of cost that they need for manufacturing with their process line. Do they need to change their process line? What's the investment they need? Are they willing to do this investment? Are the materials readily available where they want to produce? Wow. It was a big mess.
It's sensitive information partly.
Exactly. With a lot of different interests, sometimes in contradiction.
And Raquel, how did you do it?
From ALMA point of view, for us, crash is the focus, obviously, and we part from the full vehicle design, because for us is the most important. So I explained before, for Mondeo, combustion engine was the baseline. We translate to a battery electric vehicle. So we have this first version of the full body in white and closures, and we pass all the simulations, and then we start to changing the material. And in this case, obviously in parallel, there was the development of the material and the characterization of this new material, but we were changing. Okay, we are going to reduce the width of this part from 1.5 to 1 because we are using this other steel that it works well. But for us, the full body vehicle was the first point, and then we go behind to be sure that the materials are working, we are characterizing well.
And did you do this only on the components you developed for the demonstration, or also for, you said that you substituted 150 parts with the new materials?
But the virtual simulation is made for all vehicle, obviously. For the full vehicle, all crashes, lateral, frontal, and all. And it's clear that for the characterization of materials, we carry out physical tests at level component, material and level component, and the subsystem correlation.
And the 160 kilogram you saved relates into how much saving on vehicle level?
The total of kilos, I know the data, but I think 150 more or less, I'm not sure.
You said 160 kilograms you saved, but how much is it on vehicle level in percent?
In the full vehicle, I'm not sure, but I can guess that 22% in body in white, maybe 10-12% in the full vehicle. Okay. Maybe, I'm not sure. It depends, but you know, now the components in interior vehicle, seats and all this, they weight a lot.
Okay, as I said, 2 rounds of questions. The final question from my side, unless we have some additional question, is what are the further research needs in terms of, let's say, eco-design of vehicles, considering particular circularity, end-of-life strategies, decarbonization? Where do you see the major challenges and research needs?
For me, there is a key point, and maybe there are, I know that there are people don't agree and others yes. For me, if we are thinking in electric vehicles, we think in to develop a real electric vehicle. I mean, not all, but most of OEMs take the current vehicles, the IC vehicles, and they change something to become electric vehicle. But I think we need to develop one real electric vehicle from a white paper, from zero, because I think it's really different. The behavior of the in crash, the different requirements is not the same absolutely. And I think the faster and the easier way is
in the way that we are currently doing, from the cars we have to adapt to the batteries. But I think that we have to stop, think from white paper, and maybe the future cars will be different. For me, from my point of view, is the most you can say different point or relevant point we have to address in the next future. If we are thinking in electric vehicles, obviously the same if we are thinking in hydrogen to have the new vehicles.
Okay, and Lucia?
Well, you mentioned some very interesting points, and I kind of agree with Raquel from the point of view that perhaps a change in paradigm, in design paradigm, might be interesting to evaluate, okay? Because we don't know if you start, I don't know, creativity from scratch, what will be the final design of your electric vehicle? It doesn't have to look like it looks now. But that might be a little bit too far away and a little bit too risky, perhaps, to implement. Some other considerants that are very interesting for research in the future. It's a tricky question because I believe you are in a bit of a cross point or crossroads, specifically regarding the automotive industry for these next years. From my point of view, it's a very fast advancing market. In the past 5 years, we've seen some really impressive changes, and we've seen so many different OEMs migrating to the electric market. Okay, they are obliged to. We've seen a lot of competition that comes from China, who's producing some very interesting solutions for electric vehicles, and they are definitely going to grab a share of the market. So we need to see if from Europe, from here, we are able to give a good response to what's been done on that side. How are we going to do this? It depends on us. Obviously, as I said, a change of paradigm might be a groundbreaking response. I don't know if we are able, as an industry and as a research community, to provide that. I hope so, but you never know. But aside from that, I would say you need to focus. I would focus more on innovation actions where you can implement solutions really close to what the industry needs, because the industry is going to change so much in the next years. They are on a race to see who gets there first, who gets there furthest, who gets the farthest away, okay, with the best results closest to the consumer to grab a biggest share of the market, or the biggest share of the market. How are they going to do this? Our experience, at least in the consortium with Stellantis, is that implementing innovation right now on specific components or on specific parts of your car is a really tricky process, because you go to a design team and you say, you know what, I have this material and I know that it's going to give you a good performance and that it's going to lightweight, I don't know, your whatever part of your car, and I need you to implement this in the numerical simulation, okay? And they ask, okay, do you have all the material data for this? No, but I'm going to have it in about 3 months. That's the case for fatigue specifically, okay? And when they hear this, what? But I need to produce this today. It's like next week, I have deadline. So a lot of innovation actions, a lot of innovative solutions, they don't even make it to be analyzed in your OEM manufacturing process or evaluation process, because they are not fast, they are not readily available. So I would focus the research on what we can bring really, really fast to the industrial companies to implement tomorrow, I would say.
Okay, thank you very much. Further remarks? There's one remark in the back.
Yes, hello to all of you. Sébastien Piret from Michelin. Very interesting presentation with actual impact. This is very interesting for me. My question, and it will come back to what Lucia you just said. Automotive industry is a capex intensive industry, low margin, very strong relationship between tier 1 and OEMs, and sometimes even though the numbers are very attractive and appealing, it's very hard to change what's going on actually in the factories. So from your point of view, what are the main roadblocks that prevent pushing appealing and attractive new materials in the actual layout of the factories?
Oh, okay. Inertia. inertia is the main roadblock, because when you go to a specific person, you know, a specific there's a chain, right, of people that need to be involved in the decision making, in the actual implementation, testing, validation, etc. When you go to somebody in this chain, a specific player in this chain, and you tell him, no, you need to start, try this, come on, I mean, I have this material, I have this process, it's super interesting. The first thing they are going to say, what are you talking about? I mean, I've been doing my job here for the past 5-10 years, and I know things worked. I'm comfortable in the position that I'm in. Perhaps I have a lot of responsibility. I'm well seen. I don't want to risk. I don't want to risk. So inertia and low tolerance to risk, I would say. But I also understand this position, because either one of us, if we are in this position, are you willing to be the disruptive element? I don't know. I don't know. So I would say that first, changing a little bit the conscience level at the upper part, you know, where the whole decision-making scheme is done, and because decisions come from above, and if your superior tells you that you need to try this material because, and you need to implement this process because it's going to yield potentially a good result, and they're willing to make the time effort and the money effort to have you test this, okay, you're going to face this with a different perspective, obviously. So conscience from above, which is already in place right now, because everybody knows, come on, all the OEM know that this, we are living very interesting times, very challenging times, that you need to be courageous. If you are the first one to push a specific innovation, and it turns out that it's groundbreaking, you're going to be the first one to grab the market. So there is a little bit of I would say, desire to explore, okay, and to try out things. They already changed a lot of things moving to the electrification. All of the engineers, well, I'm being a little bit dramatic, not all, but a big part of the design companies that were previously, in the past years, focused on mechanical behavior and stuff which were related to the combustion engine, nobody's working on that right now. Everybody's working on electrification, okay? So already there was a change in paradigm, and people know that they are going to have to risk a little bit. Maybe we are going to make it past this barrier of low tolerance to risk. I hope, I don't know.
Let me know to add only one comment. I think the key factor is regulation. It's clear, because in our sector, everybody wants to, well, in all sectors, everybody wants to win money. And if we are good, and we are in a position that it's fantastic, it's okay for everybody, but at the end, we have the regulation. And now, Lucia explains, electric vehicles are there, and why are there? Because regulation says that we have to be aware. And more quantity of recycled materials will be there. Why? Because regulation told us that we have to. So it's mandatory. It's not, well, not in all cases. It's true that there are some brands and OEMs that decide, take decisions in terms of to be more aligned with the environmental impact, or because they have ethical points, important points. It's true. There are some brands that this is important for them, but in general, regulation is the key point to push up and to go, and we have to accept, and we have to evolve to be able to answer this. And in this case, it's really it's true that it's a big challenge to be able in Europe to answer this in the opposite to China, because the regulation for China and for us is not the same. It's true that if these Chinese vehicles are going to be sold in Spain or in Germany or in France, they have to meet our requirements, but we can say that the basis of the play are not the same. So it's really difficult in this case to be able to meet all the requirements.
but it's, I think, it's the challenge.
So you brought up an interesting point for a lot of discussion. I think there are many in the room which do not agree with you. Regulation can also be hindering innovations, so be careful. But it's good to see that we have here dedicated, passionate researchers striving to solve our challenges in transforming our industry. That's really good to see, and I'm pleased that we have this lively discussion. We are only 2 projects and we took up all the time, so thank you very much for your contribution in the discussion and your honest answers. Much appreciated, and I also would like to thank the audience for joining. Yeah, maybe some last words from your side, Eric?
No, I just want to thank everybody, the presenters, you, Thilo, and as you said, the audience that contributed to the discussion. In the end, we started from a very technical discussion, and then at the end it became almost a philosophical discussion about regulation and everything.
Yeah, it's good.
So, no, thank you for everybody, and I think we have reached the end of the session, and we can move out of the room and enjoy a coffee. So thank you, and enjoy also the rest of the morning and of the conference. Thank you.